Hello and welcome to this lesson on basics of electrical services. My name is Will White. I am a curriculum developer and instructor here at Solar Energy International, and I will be your presenter for this lesson. In this lesson, we are going to talk about the basics of electrical services. Who would have thunk it? We're going to talk about some fundamental concepts when we are talking about the most common electrical services, and we're going to go over the electrical services that we typically see here in the United States, including services such as single or split phase services that we typically see in residential systems. And we'll also discuss a couple of different types of three-phase services, specifically three-phase Y and three-phase delta, which are more common in commercial situations. We're also going to talk about what you need to look for when you're going onto a site during a site evaluation, and what you need to look at and what information you need to collect and record so that you can design a system that is going to be compatible with the electrical service on the site. First, a general disclaimer. NEC Article 100 says only a qualified person should be working on electrical services. And keep in mind that the courses that SEI provides are really introductory level information. Even courses like the one you're taking now, which is an advanced design course, doesn't give you the hands-on experience that you need to be able to safely work on these types of systems. You really need to go out in the field and work with someone who's trained, experienced, most likely licensed, who can show you the proper and safe ways to work on these systems. In many jurisdictions, you can't open an electrical service panel without being a licensed electrician. Of course, that's going to vary depending on where you're at, but you can actually get in some pretty big trouble in some jurisdictions if you're doing electrical work without a license. So, develop your skills, make sure that you can elevate your knowledge and experience to the level where you can identify hazards related to the electrical systems that we're working on and know how to mitigate those hazards. Let's talk about what a service is. The National Electrical Code Article 100 definition says that a service is the conductors and the equipment connecting the servicing utility to the wiring system of the premises served. Basically what that means is that the service, quote unquote, is all the equipment that's between the utility and the wiring in the house. That could include the wires that go from the transformer or the pole out at the street in and to the meter, like we see here in the picture. We've got conductors that are coming through this conduit that come from the pole at the street and go into this meter enclosure and connect to this utility meter here. Now, what consists of the service is going to depend on the utility that you're working with, and what is owned by the utility and controlled by the utility and what is controlled by the building owner are going to vary a little bit depending on the specific utility. Most utilities, in my experience, that meter enclosure, the meter can, and the meter itself are controlled by the utility. Most of the time the utility won't actually pay for it. You have to buy that equipment, or at least the meter can or the meter socket, but the utility usually does not want any work going on inside of that box except the wires coming from the utility to the meter and the wire leaving the meter enclosure and going to the main service panel. So they usually don't allow you to do any connections inside that meter enclosure. There are, of course, some exceptions to this rule, so you want to check with your utility and what their requirements are there. The primary source of electricity as defined in NEC 705.1 can be multiple different things. It could be the service from the utility, and the term service only comes from a utility. It wouldn't come from anything else. But that primary source of electricity could come from the utility, but it could come from other things as well. In a microgrid, it could come from a generator, it could come from battery storage, could come from a PV system. There may be systems like many village systems that only have fossil fuel generators, so that primary source of electricity would be that generator or generators. In my house, I live off the grid, so I have a standalone inverter. That is my primary source of electricity. I have no utility connection, so the wires come from my standalone inverter and go to the main disconnect in my main service panel, and that's my primary source of electricity. Now, a couple of things I wanted to note in this equipment here. Again, you've got wires coming from the utility up into this meter base here. They would land in some lugs in the meter, typically in the top of the meter. And then the lugs at the bottom of the meter base go out through this little connector here and into this main service panel. The meter clips into the base. This meter has a locking ring, so it's locked in there so nobody can remove that meter. In this main service panel, this top 2-pole breaker that has the little screw right there attaching the breaker there, that's our main service disconnect and overcurrent protection device. The screw affixing the breaker to the service panel is there so that you can't remove that breaker and still have it energized from the utility. If you were to do that, the terminals on the back side of that breaker would still be live, so there'd be an electrical shock hazard there. And of course, we don't want to have that happen. One of the basic parts of a utility distribution system is the transformer. And a transformer simply changes voltage from one level to another. So it's either stepping voltage up from a low voltage to a higher voltage, or it's stepping voltage down from a high voltage to a lower voltage. Each transformer has two sides, a high voltage side, which is commonly referred to as the primary side, and a low voltage side, which is referred to as the secondary side. Now, we at SEI prefer to use high and low voltage describing the two sides of the transformer because primary and secondary don't really tell you which side is which. Depending on the situation, the high voltage side may be the primary or the secondary side, depending on the application. Here on the right-hand side of the screen, we see a typical diagram. This is an electrical diagram of a transformer. We have the high voltage side on the left in this case, and we have the low voltage side on the right. A transformer is an isolated device. So the high voltage side and the low voltage side are not electrically connected. The only connection between the two is a magnetic connection between the windings in the two sides. Now, the number of turns in that winding is what dictates how the voltage is stepped up or stepped down. Really, the purpose of the transformer is to change voltage from one voltage to a different one. A good example would be a step-up transformer in a utility scale system. Maybe we have a 600 volt AC output on the inverter in a utility system, which is pretty common voltage, and we're going to step that up to a medium voltage distribution voltage, maybe 36,000 volts, something like that. It varies depending on what we're connecting into, but that would be a common use for a transformer. We also see transformers in the distribution system where we're taking a three-phase voltage out at the utility pole and stepping it down to a single or split phase voltage that would be used in a residential house, for example. So we see transformers used in a lot of different applications related to the utility grid. There are several different parts of the utility grid. We're going to start on the left-hand side of this slide with power generation, which is typically fed into the transmission system at a high voltage. Transmission is the big towers that you see across the country where the energy is being transmitted over a long distance from the generation to the consumption. Those are typically at a very high voltage. Then we get into the medium voltage distribution system, and those are the more local distribution poles. And then we transform down to the end user service voltage. So that would be the lower voltage that's going to be used in a residence or commercial building. And when we talk about voltages, they are going to vary depending on the situation. Our typical transmission and distribution voltages are going to range anywhere from 69 kV or 69,000 volts down to 4,000 kV or 4,000 volts, and kind of anywhere in between depending on the situation. Our end user voltage is going to vary depending on what type of application we're talking about. In the United States, our common residential voltages are 120/240, which is a single phase or split phase service. We also have three phase voltages, which are more common in commercial buildings, 208/120 or 480/277. We'll talk about both of these in a little more detail. In other locations around the world, you'll get different voltages. 400/230 is a common voltage. 380/220 or 100 or 220 or even 250 volts. Those are common voltages we see in different areas. It's important to know what the voltage of the service that you're going to be working with is, so that you can match that voltage to the electrical equipment that you will be working with. An important thing to note here is that our PV systems can be interconnected at any point in this distribution system. They could be at the transmission level, at the distribution level, or at the end user service voltage. So we can see them connected in many different places depending on the application. With distributed generation that's going to be used directly on site, connected on the user side of the utility meter, those will almost always be connected at the end user service voltage, so 120/240 or some variation of a three-phase service. Larger systems, like larger commercial systems that are connected with their own service, or utility scale systems, will most commonly be connected at the medium voltage distribution level, and every once in a while at the higher voltage transmission voltage, but we'll typically see that at the distribution level, which is often referred to as medium voltage. Let's take a look at 120/240 AC split phase, which is commonly referred to as a single phase service. Now, we've talked about a transformer, and we have the diagram of the transformer on the bottom left hand side of the screen here. You can see the high voltage side is on the left hand side, the low voltage side is on the right. And the large diagram in the middle here is only showing the right hand low voltage side of this bottom diagram. So we're only seeing half of the transformer in this main diagram here. We can see in this service, the 120/240, we have two lines, L1 and L2, and then we have a neutral in the middle. Now, if we test from line 1 to line 2 in this service, we should see somewhere around 240 volts. Now, it's not going to be exact. It's not going to be right dead on 240 volts in most situations. It's going to vary somewhere a little, typically between 238 and maybe 242, maybe 44 volts. Usually it's a little bit higher than 240 volts, but that's what we would typically see when we measure between line 1 and line 2 in a 120/240 split phase system. Now, if we take our meter and measure between line 2 and the neutral conductor, we'll get 120 volts, and we'll see why we get that in just a second when we look at the waveform for this service. We would get the exact same thing if we measured between line 1 and the neutral. Now, in this type of service, we have a service grounding connection. So the service is connected to the ground at one point where there's a connection between the neutral conductor and the grounding system in the building. So that's our connection between the green equipment grounding system and the grounded conductor of our AC system. This is a solidly grounded conductor. That's our white neutral in most cases. Since the neutral conductor, the white wire, is directly connected to ground, or the grounding bus bar, the green wires in the system, or the bare copper wires that go down to our grounding electrode conductor or our ground rod, the potential between the neutral conductor and the grounding system is the same. So if we tested between line 1 or line 2 and ground, we should get the same result that we do when we're testing between line 1 and line 2 in neutral, because the neutral and the ground have the same potential. Let's look at a waveform of our 120/240 volt split phase system when we are measuring these two waveforms and we see the red conductor, the L2 in the red waveform, and the black conductor L1 in the black waveform. The voltage of this system is cycling between 120 volts positive and 120 volts negative. Now, these two conductors, L1 and L2, are directly offset by 180 degrees. That's why when we measure, we're measuring from the peak here to the peak at the bottom. So when we measure between L1 and L2, we're measuring exactly 240 volts, which is the 180 degree offset. Now, this is showing one cycle, which is measured in hertz. In the United States, our systems are operating at a 60 hertz system. So there are 60 of these cycles per second. So 60 times per second, the voltage goes from 120 volts to 0 to a negative 120 volts on each line. That's how an AC system works. Again, when we measure our voltage, line 1 or line 2, measuring between those two, we're always going to get around 240 volts. When we measure line to neutral or line to ground, we will get 120 volts because, again, that neutral is bonded to ground at one point in the system, so they have the same potential. Now let's look over on the right-hand side of the slide at this diagram of a main service panel. We have 4 wires coming in from the utility meter. We have the green or bare copper grounding conductor. That's our equipment ground. In this case, this is the wire going to the utility meter. In most cases, it may be going to the grounding electrode, in which case it would be a grounding electrode conductor. We have our 2 ungrounded conductors. They are not connected to ground at any point. So that's our black L1 and red L2. And we have our neutral, which is our grounded current carrying conductor. Now, again, that neutral is connected to ground at one point in the system. This diagram shows a main bonding jumper, which is a green screw, which is connecting this isolated bus bar for the neutral conductors to the metal box of the enclosure. And that metal box is electrically connected to the non-isolated bus bar that is connected to all the equipment grounds in the grounding system. In some cases, you'll actually have a metal copper jumper between the neutral bus bar, and it will go across and into the equipment grounding bus bar or the ground bus bar there, and that would be our system bonding point. Now we see these 2 bus bars here, and each bus bar has a little finger. Every other finger is connected to a different bus bar. So we start with L1 and then L2, L1, L2, and they alternate as we go down the bus bar. So as we add breakers in here, a single pole breaker connects to one of the bus bars. So when we lock that breaker into the service panel, it automatically connects to the bus bar. In this case, it just happened to connect to the L2 bus bar. When we connect a 2-pole breaker, by design, each side of this breaker connects to L1 and L2. Which ungrounded conductor is connected to which terminal in the breaker depends on what position that is in the panel. If we moved this one up one slot, it would be connected to L1 and L2, where here it's connected to L2 and L1. That doesn't usually make a difference. The reason that it alternates between the two ungrounded conductors is to balance the loads evenly between the two phases of this split phase system. So L1 and L2 would get an even number of loads in theory. In these 2-pole breakers for a 240 volt load, we want to make sure that it's connected to both L1 and L2 so that we are getting both of those phases into that 240 volt load. That's really important. We wouldn't want both of the terminals on that breaker connected into one phase of that system because that load would not operate properly. Okay, that's the end of part 1, the overview of split phase services. In the next part, we are going to take a look at some different types of 3-phase services. So join me for that part when you're ready. Thank you very much.